Okay, so in this video, we are going to walk through an example of doing a hypothesis test on the difference of two proportions. And so the example that we'll take a look at is there's an artificial sweetener called xylitol, and researchers believe that this sweetener might actually help prevent ear infections. So before we go any further, let's just kind of consider what their claims are here. And so these researchers, we'll include ourselves with them, they believe that xylitol is going to reduce the incidence of ear infections compared to no treatment. And so setting up the hypotheses to reflect those claims, I'll do it up top here. The null hypothesis would be that the proportion of people, of all people, that take xylitol that get, or in this case children, that get ear infections, minus the proportion from the control group that don't take anything, there's no difference. So this sweetener doesn't change how likely somebody is, or a child is, to get an ear infection. And we're going to compare this to the claim in the alternative that if you take this sweetener xylitol, then actually you're less likely to get an ear infection. So the difference of proportions in the proportion of people or children that get an ear infection that take this sweetener is going to be less than the control group. So we would say this difference is less than 0, and that's going to imply eventually when we do our test type, we have a left tail test, so we're going to use less as that argument. But in part A, we're first asked to calculate this test value by hand, and so that means in part A, we're going to use the formula for the test statistic, the standardized test statistic up top. So we have, in this case, a sample proportion from the treatment group, the xylitol group, so that had 46 out of 159. Which I'll round this off to 3 decimal places. That's about 28.9% of the children that were on xylitol got an ear infection. And now let's compare this to the control group, which had 68 out of 165. And so that comes out to a proportion which is about 41%. So rounding to 3 decimal places, that's 0.412. So this does seem like a pretty big difference in proportions. But is that difference actually large, or is that within the realm of difference that we might expect from just the sampling process? So then on top, I'm going to take my sample treatment group, which had a 0.289 proportion that got an ear infection, minus the control group. And then we're going to divide this by the approximate standard error. So we would need to calculate the pooled proportion to do this. This is this p hat p value. So to calculate this p hat p, our pooled proportion, I would say that altogether we had 46 plus 68 children in our study that got an ear infection out of the total number of people, which if we combine them together was 159 out of 1 and 165. And so that pooled proportion, as you would expect, is going to be somewhere in the middle between our treatment and control group. So that's what we're going to use when we calculate this standard error. So I've got 0.352 times 1 minus 0.352. And then we're going to multiply this by 1 over n1, which is 159, plus 1 over n2, which is 165. So doing that calculation very carefully, comes out to a test statistic of minus 2.317. Okay, and then our p-value is going to be what's the probability that we would get a difference even more extreme. So in other words, that p hat x is even further below p hat c. And that would mean that we would get a test statistic which is even more negative than the one that we observed. And so the picture of what we're doing now is we have this standardized normal distribution, which is describing our distribution of differences in proportions. And we observed a difference of minus 2.317. So the p-value is going to be all of this area in the left tail. That's why we call it a left tail test. And we could either use a standard normal distribution or the p-norm function in R, where I would enter the value, and then the mean of the standardized normal distribution is 0 and the standard deviation of 1. And that's going to calculate that this area over here is about 0.0102. And that's telling us how much area is over here. So that's what it would look like if we did this calculation by hand. But now let's use this convenient proportion test function that is built into R. And so in this case, the input would be our first proportion in the way that we set up our hypotheses was the xylitol group. So we're going to first put how many people in the xylitol group were a success, which in this case is an ear infection, how many in the other control group got an ear infection, how large was our treatment group, how large was our control group, and then our alternative hypothesis, recall, is we were claiming that xylitol is going to reduce the incidence of ear infections. So it should be less than the control group. And entering this into R, we get the following output. And so from all of this, what we can see is what we're most interested in is the p-value. And that we see over here. And if we compare that to the p-value that we got, it's a little bit different. In fact, it's a little bit greater than the p-value that we got from our approximation. So let me just say that if we're looking at this and you're wondering what the difference is this method uses what's called a continuity correction, whereas the way that we did it initially does not. So in the very last video, I'm going to come back to this example and we're going to redo part A with this continuity correction and see what the difference might be. But over here we can see that this is the proportion from the xylitol group. Here's the proportion from the control group. And we really don't want to make any sense out of this 95% confidence interval in this case because we had a one-tailed test. And we actually don't see what the test statistic is anywhere in here. But we just need the p-value in order to make a conclusion, so we don't need to see the test statistic. So we've got a p-value of 0.0398. And so if we want to make a decision and summarize our results, just recall over here, we're using a significance level of 1% in this case. So using a 1% significance level to make this decision is we've found a p-value which if we use kind of this more accurate method, 0.01398, which is bigger than the significance level of 0.01. So when that happens, the test is not statistically significant, and here we fail to reject HO, and the test is inconclusive. Okay, and so even seeing a difference that was seemed quite large over here, if we set a low bar for the significance level, or I should say like a high bar, the lower we set alpha, the more stringent our condition is in order to reject the null hypothesis. And we didn't make that condition. So here, based on this research, this would not be enough to come out and say like people should take xylitol to reduce ear infections. We don't have enough evidence to claim that yet. And so let me just conclude this one by saying that when we did this by hand without the continuity correction, it made a difference almost to the point where we would have changed our decision, but not quite. So if we don't use this continuity correction, we are going to be off a little bit when we do our calculations by hand. So on this very last slide, I just want to walk through what that continuity correction looks like when we do things by hand.